Hi, this right here is the royal game of It's one of the oldest board games in the world. It might actually be the oldest game in the world where we know the rules. Game boards like this one and the dice like, well, these things here and the one which just fell on the floor, triangular dice. I guess they are technically D4s, though our Bronze Age ancestors didn't call them that. Dice like this and game boards like this have been found in the Royal Cemetery in the city of Ur. You know, the Bronze Age city where some guy named Abraham came from. And the other game boards and the clay tablets describing the rules have been found all over modern day Iraq. And that's why we today can play this game just like our Bronze Age ancestors used to do. The only problem for me is that this is a two-player game and I don't have any friends. So I don't have anybody to play against. But thankfully some American billionaire lizard said that actually computers is a perfectly adequate replacement for friendship. So I have decided to make this game on my computer. And the actual rules probably varied a lot from place to place and over the roughly 2000 years where this game was popular. But the rules I'm going with here are the ones translated by the British historian Irving Finkel. So the board looks like this. There are a bunch of tiles and each player have 7 pieces. The goal for me is to move my pieces from my start here all the way to the finish here. Your goal is to move your pieces from the start here across the middle and all the way to your finish here. And the way we move is by rolling these tetrahedron dice. These dice have well, a bunch of painted tips and unpainted tips which can either point up or down. If I roll the dice, you see I have 3 painted tips pointing up. That means I'm allowed to move one piece 3 tiles. Right now I don't have any pieces on the board, so my only choice is to move a piece from the starting position 1, 2, 3 here. And now it's your turn. Well, it is your turn unless I happen to land on one of these Rosettas here. If I land on one of these Rosettas, or if you land on one of these Rosettas here, you get a free turn and you can roll your dice again. But right now it's your turn. Let's see what you get. 1. How embarrassing. You can only move to this position here. Now now it's my turn. Let's roll again. 0, no, 1. Well, now I get a free turn because, well, I could totally choose to move a piece here, but I would much rather get a free turn by moving here. Let's see, it's my turn again. Another one. Well, normally I would move a piece here, but for demonstration's sake, let's move a piece here. And you know, let's just pretend you have rolled a 4. That's the best possible roll you can get. Now you can move this piece. Now you have an interesting choice to make. You can move a new piece onto here and get an extra free turn, or you could move this piece here and take my piece and knock it back home. I don't know what you would want to do, but for demonstration's sake, let's say you took my piece here. That's a thing you can do if I am in this combat zone, unless I happen to be standing on this Rosetta here. If you are here and have rolled and it's your turn and you had rolled a 4 and I was here, you wouldn't be able to take this piece. In fact, in this case you wouldn't be able to do anything at all, because the only other choice you have is move a new piece onto the board, but that's blocked by your own piece, and since I'm on this Rosetta, I am safe. I cannot be taken by you, so you actually have no legal moves in that case, so you just lose your turn. The same thing would happen if, say, you were here and you also had another piece here. If you had rolled a 4, you are not allowed to have 2 pieces on the same location, so you wouldn't be able to make this move. In this case, you would be forced to make either this move or this move. I think that's all there is for the rules. Apart from finishing the game, when you move your piece to the finishing location, you have to move them exactly to the finishing location. That is, if I stand here and I roll a 4, that's no good. I cannot finish the game because I need a 2 to finish from this location here. I either need to stand here and roll a 4, stand here and roll a 3, stand here and roll a 2, or stand here and roll a 1. I think that's all there is to say for the rules. The rules are really rather simple, but it still makes for a fun and extremely hectic game. Now, with the rules out of the way, let's code the game. Let's start by just coding a version of the game where 2 humans can play against each other on the computer.
So, the first thing we need to do is find a way of representing the way the state of the game on the computer, the way the board looks at a certain point in time. And this is how I'm going to do this. I'm going to use 33 16-bit integers to represent the state of the game. And the way this works is that the first 16 numbers represents the number of pieces the first player has at each location on the board. So in this case, the first player has 5 not yet started pieces, so there is a 5 in the first number. They have 1 piece in the second tile on the board, so there is a 1 in number 2, counting from 0, which is actually the third number. And they have a piece on this Rosetta just before they finish. That is number 14, counting from 0. So there is a 1 in number 14, counting from 0. The other player also has a number of pieces on the board, and they are represented by the next 16 numbers in this 33 number list. The first of these next 16 numbers, number 16, represents the number of pieces which the other player has not yet started with. In this case, that's a 4, so there's a 4 in number 16. There is a 1 in number 17 because there is a 1 piece here, and there is a 1 in number 21 because they have 1 piece here, and they all have also finished with 1 piece. So number 31 has a 1 in it. The final number represents whose turn it is. This being 0 means that it is the first player's turn. If it was a 1, it was the other player's turn, black in this case. So just to summarize, there are 5 not yet started pieces for player 0. That's a 5 in number 0. There is a 1 in number 2, and the number at number 14 is 1 because there's 1 piece here. Same goes with the 17th and the 21st and the 31st number, while the 16th number is 4 because the other player has 4 not yet started pieces. So that's how we can fairly easily represent the state of the royal game of on the computer. you might argue that you could do better than this, and I know you could. I know for a fact that it's possible to compress this way more, because most of the tiles can only have a single piece, so you could get away with using a single bit for that. And even if you don't want to do bit shifting magic, you could use 8-bit numbers rather than 16-bit numbers. But I'm using 16-bit numbers because otherwise I would have overflow issues later when I try to calculate the value of each position, and I would need to explicitly insert a lot of casts, which takes time. The program is just faster if everything is 16-bit numbers to begin with, and I am optimizing for speed, not data storage. So that's why I'm starting the game like this. But now comes the question, how can the computer figure out what happens next? Let's say it's my turn, I'm white and I rolled 3. Well, just looking at this game you can tell that I have two options. I can either move a new piece from position 0 to position 3, or I could move the piece from position 2 to what I call position 5, which would take your piece at your position 21. How can the computer figure that out? Well, we need some kind of function which calculates the number of possible moves and calculates what the game will look like after each of these possible moves. And here it is. It is actually not very complicated. I will go through how it works in details shortly, but for now it's worth pointing out that it returns an integer number of legal moves, and it doesn't return a list of legal moves. It modifies an existing list of future games. The reason I'm using an existing list instead of creating a new list is again for the sake of speed. It is expensive in terms of execution time to allocate a new list of numbers. It's slightly faster to use an existing workspace. So that's what I do. As for the rest of the function, it basically loops through every single tile on the board, including the tile containing the not yet started pieces of whoever's turn it is, and asks for this tile here, can I make a move with this roll here? In that case that would be a yes. In this case that would be a no, because there are no units on this tile here. In this case that would be a yes, and we also check if we need to take a piece. Then we check for every single tile if the player whose turn it is has a piece on this location, and if it has, if it is legal for this tile to be moved. In well, this case it's not. And that's basically how the function works. It's a pretty simple function, and more importantly it's a fast function. It takes on average 70 nanoseconds for it to calculate all future possible positions, all future possible states of the game, which is fairly quick, all things considered. So having this get future games function, all we actually, and a way of representing the games, all we actually need to make the game on the computer is a way of picturing the game. And oh look, one appeared right here. This is a very simple console implementation of the Royal Game of Earl. The current state of the game is represented by text in the console, and apart from that we need a random number generator to actually make the rolls. And as you can see, we also have got that. It seems I just rolled a 1, and according to this little 0 here, move number 0 I can make is move a piece from my unstarted position to this position, and there aren't any other legal moves, so let's just write I want to make move number 0. Now I've got a piece here. Now it's your turn. You rolled a 2 and you can only make move number 0, which is to, in this case, to move one piece from your unstarted to this position. Let's say you want to make, well, I could write move number 1, but that move is out of range, so I have to write move number 0. Okay, now it gets interesting. I rolled a 3. I can choose to move here. That will probably mean move from the unstarted to here, or I can choose to move this piece here. That's move number 1. This is just how I visualize different future possible states, and I kind of want to end up on the Rosetta, or in this case on the star. So let's write 1. I want to make move number 1. That should move this thing here. There we go. Now it's your turn. No, it's my turn. I want to move from here to here. That's move number 0 because I rolled a 2. Let's just do that, and you get the idea. This is not a very complicated game to simulate. This is not a very complicated game to make a 2-player computer game of, but as I said, I don't have anybody to play against. I want to play against the computer. So let's look at how we can get the computer to make some decisions on what to do on its own. The way the AI is going to take decisions is it's going to look at all the possible future states returned by the getFutureGames function, and it's going to assign a numerical value to each of them, and then it's simply going to go with the one with the highest or lowest numerical value depending on what player it's playing as. Say it's the first player's turn now, the white player's turn now. One possible future is this state here where we have moved this piece from here to here. Another possible future is one where we have moved this piece from here to here, here. And one other possibility is one where we have moved one piece from here to here. We want to be able to assign a numerical value to each of them. Let's take this possible future as an example. We want to assign a numerical value to this thing, and well, one way we could do that is by simply assigning one value to each tile and say give plus 4 points for having a piece on this tile here, maybe plus 8 points for having a piece on this tile here, maybe minus 5 points for the enemy having a piece on this tile here, and I don't know, minus 15 for the enemy having a piece here. That will certainly work, and that will give us a semi-functional AI opponent. But we can do better than that. I want my AI to take into account possible interactions betwixt pairs of two pieces on the board. For instance, there is a pair of pieces here and here. There's a pair of pieces here and here, here and here, and here and here, and a bunch more. The way I'm going to assign a numerical value to each pair of pieces is using a matrix like this giant list of numbers, this table with a whole bunch of numbers. And the way this is going to work is for each pair of pieces I'm going to look at whatever row and column these pieces are in. This thing, for instance, is it's number 21 if we are counting for the player or playing the black pieces. We count 16, 17, 18, 19, 20, 21. So we have one piece in position 21. We have and we have this one piece. This is, if I'm not mistaken, position 7. Yeah, because for the white player we count 0, 1, 2, 3, 4, 5, 6, 7. So we look up in this matrix in row number 21, column number 7. That will be this thing. This is minus 2. So this pair of pieces is worth minus 2 points. This pair of pieces, on the other hand, that's 21. and 3. Let's look that up. That's plus 2. So this thing here is bad for the white player, obviously, because this thing is very likely to eat this thing, but on the other hand this thing can eat this thing, so it sort of cancels out. We could also look at, say, the interaction between this piece and this piece by looking at that'll be column 3, row 31. That's a 0, obviously, because these pieces are so far away there can be no interaction betwixt them. So what I've done here you'll probably recognize as a matrix vector multiplication. It's a multiplication where we have sandwiched a matrix betwixt two vectors. In quantum physics term, the value of this position is the expectation value of this entire matrix here, given this state here. It might look all very complicated, these interactions. Oh, and there are of course also interactions between this piece here and this piece here. That's all the elements on the diagonal here. In that case 9 and 9, that would be 12 points just for having a single piece here. It might sound all complicated when I try to explain it this way, but it's super simple to code. In fact, let's take a look at that now. So it's actually fairly easy to write a get value function using these principles I just talked about. In fact, this is what it looks like. This is a nice and simple function. But there's a problem with this, and that's that it is slow. It is extremely slow to run. It takes something like 2 microseconds to run on average from my test, which is horrendously slow. And the reason I care so much about speed is I have an idea that maybe at some point I will train an AI on this game. This is not a thing I'm going to do in this video, but maybe I will return to this project in a later video and train an AI on it. And if I'm going to train an AI, it's really important that the game can run quickly. I can have 2 bots playing against each other hundreds, thousands, if not millions of times. And 2 microseconds is simply too slow. This is the slowest function in the game by an order of magnitude, literally. And I'm sure you can think of a lot of improvements already, a lot of ways you could get this to run a little faster by tweaking it here and there, but to really get this to run faster, we are going to use some dark magic, also known as low-level C. And well, to understand what we are going to do, I think it's useful to take a step back and ask what happens. Sorry for the sudden flash of light, by the way. What happens if we want to add all the red numbers to all of the blue numbers? Well, if we write some code in C or C++ to do this, it gets compiled to assembly instructions, and there's probably one assembly instruction which adds the first numbers together, then adds the second numbers, the third numbers, and so on and so forth together, one at the time. But do we really need that? I mean, we don't care what order these numbers number pairs get added in. In fact, for all we care, there might as well be a single instruction which added the entire first list to the entire second list. And as it turns out, there is such an instruction, a single addition or a single multiplication or a single comparison, which can be applied to an entire list or an entire register of numbers and give the result in just a single instruction. And this is called SIMD. This stands for same instruction, multiple data. Or was it single instruction, multiple data? I don't remember, and doesn't really matter. And these are extensions we have access to when we're working on the modern CPUs. My CPU isn't the most modern in the world. I only have access to the AVX2 register. the AVX2 extension, which gives me access to 16 so-called YMM registers, which can hold 256 bits each, so I can hold 16 16-bit numbers in a single register, and I can use an assembly instruction like VP add W for standing for word to add all the 16-bit numbers together in a single instruction. And if you have a more modern CPU, you probably have access to AVX 512, which allows you to add even more numbers together at the same time, but I don't. But using assembly is a little awkward, and I am so bad at writing code in assembly that my code will probably end up being slower than what my compiler can do anyway. So thankfully I can use AVX2 extension directly in C++ using the initrin header, as you see here. This is the getValue function rewritten, or actually only a chunk of the getValue function rewritten to use AVX2. It's ugly. It's very ugly compared to what we have before, and this is only the first about a third of the function. Yeah, it's not pretty, but it's much faster. Now it takes only on average 170 nanoseconds to do the calculation, which took 2 microseconds before, and this is a huge improvement, and this is what I am looking for. I am satisfied with this version of the getValue function. So that's how the AI is going to work. We're going to use this matrix here to assign values to each of the possible future states, and then the AI is simply going to go with the possible future it likes the best, depending if it's the white player or the black player. That's either the one with the highest or the lowest numerical value. But you might ask, where does this matrix come from? And I'm sad to say I have manually created this matrix. It did take a while, it did take a lot of experimentations, but it was actually fairly easy to do. I just, well, first thing first, I assigned the values to the diagonals, essentially the value of, for instance, what's the value of the first player having a piece in this position here. I don't know, that feels like 10, so I assigned 10 to that, and so on and so forth for all the other positions. And then I looked at possible interactions. If I have a piece here, what possible interactions do I care about? And then I set them to whatever just felt right to me. Yeah, that's not a very scientific way of going about it. I certainly wanted to do this a more scientific way. I wanted to optimize this matrix. In fact, I wanted to have a massive competition between bots with the different brain matrices, where bots would fight against each other, and the best bots would be selected to breed with other best bots and produce new small bot babies with slightly different brain matrices. Then they would compete, and the process would repeat until I had trained the very best AI through a process of natural selection. That's a fairly normal algorithm for training AIs, but as you can guess, that didn't quite work out as I planned. The optimization landscape is simply too complicated, and there are way too many variables. Let's see, I've written down how many. I think 561 variables to work with, and that just turned out to be too many, and it takes way too long for two bots to play against each other a statistically significant number of times. This game is, after all, very much dictated by randomness. We really have to play against each other 1,000 times before we can say with certainty whether you or I, or in this case whether bot A or bot B, are the best at this game. And even though each individual game only takes like 10 to 100 microseconds, 1,000, 10,000, 20,000 games takes a long time, and that's just to compare two bots. If I really wanted to hold this bot competitions, I would need hundreds, if not thousands of bots, and that simply takes too long to train. So that's why I stuck with this human-generated matrix. Maybe if I feel like it, I will return to this project later and see if I can maybe do something with the neural networks. That would be fun for another project, but for now we are stuck with this human-generated matrix. Okay, I guess it's time to show off the results. I've set up a game here where I'm playing as the first player, player 0, and the bot is playing as player 1. Using the brain matrix I generated, let's see, I have rolled a 1, choose which move I want to make. I want to make move number 0, the one where I move from here to here, because that's literally my, my only choice. Okay, the bot rates move 0 as -18, and it chooses to make move 0. So not only does it tell me what the bot has decided to do, it has decided to apparently move one piece to this location here from the start, since it rolled 2. It's also telling me what value it assigns to this, and remember, a negative value is a good thing for the other player, player 1 in this case. Press enter to continue. Okay, now they got one here. I rolled a 3. I can choose to either move here, that'll be move 0, that'll be from here I guess, because no, that'll be from here, or I can choose to move to the Rosetta. I'm obviously going to go with the Rosetta, so let's take 1. Oh, I get another roll. I rolled 2. I can either move here or I can move here. I'm going to move here because this feels a little risky. Okay, bot chooses move 1. They rolled a 1, so they're going to move here. Okay, I guess you get the idea. Now it's my turn. I rolled a 3. I can move either here, here, or here. You get the idea. I have a functioning bot I can play the Royal Game of against, and that was what I set out to do in this project. So I guess the video is over. Maybe I will return to this project someday with armed with the neural networks and make a better bot train itself. But for now, I want to thank anybody who made it this far in this video, and I want to sincerely apologize for the atrocious audio quality in this video. There ain't really anything I can do about that. So farewell, and feel free to hit any random buttons down there on YouTube. I don't think they do anything, but it's at least satisfying to press buttons. So bye!